Sharma from the Uppsala University in Sweden. We have a brand new audio-visual system in this room, so we are the pilot group for it, so we appreciate the help. You want to check your volume?
Thank you very much for this opportunity. This is an honor to share some of our observations with you. Actually, my previous speaker has told everything that I wanted to tell you. But I will add one more thing. That when nanomaterials are in the body and the body could be diseased, then it could have entirely another effects. So I'm showing you some of the in vivo experiments with us, and I can tell you that this is a multi-organizational cooperation at different parts of the world. I am from Uppsala University, and obviously I have to declare that all these are mine. Nowadays we have importance of nanomaterials because nanomedicine is coming more and more. And the idea is that, as stated by the previous speaker, that we do not know how nanomaterials are behaving in the body, in a biological system. So it's already mentioned that size is important, types also important, but I'm showing some of the results that there are other factors also important. For example, your external factors, means environment or pollution, and also the internal factors. For example, you have cardiovascular disease, diabetes. They are all included in the effect of nanoparticles, and that is our research in vivo situations in various organizations. I started my work on blood-brain barrier, and this is an honor again to be NIH. This is Dr. Rappaport, who was one of the pioneers, showed blood-brain barrier in physiology and medicine, and the book was published in 1976. And I have another honor for him, that I did a PhD thesis in Banaras Hindu University in 1982, and he was very kind to examine this thesis, and obviously he recommended for the award, and this is my supervisor at that time, Professor Kumkere. So I have interest in blood-brain barrier, and therefore I believe that blood-brain barrier is the key for all kinds of brain diseases. I am focusing largely effect of nanoparticles on the brain. So as you know that endothelial cells that are the physical constituents of the blood-brain barrier, they are highest in number, much more higher than neurons. So what they are doing? So we have highlighted in a book that the importance of blood-brain barrier is quite important in all kinds of neurological diseases. And I was having another honor that Dr. Milton Brightman from NIH, he wrote the foreword of this book, because he was the pioneer. First time he showed that the tight junctions between the endothelial cells are the anatomical seat of the blood-brain barrier. I am basically a neuropathologist, so I look all the structures in forms of neuropathology at light and electron microscopy. This is my mentor in Uppsala University, Professor Inge Olsson. Then I met with Dr. Sharma. He is one of the leading electron microscopists in Germany, and I did some training with him. So that is a mixed background. But we believe that any kind of insult to the central nervous system opens the blood-brain barrier, making lots of changes and leading to cell death, where nanoparticles are fitting in this program. The point is that either they are affecting the initial results, or they are affecting at this level and in all the levels. This is our hypothesis that we are trying to prove or disapprove. We highlighted this importance of nanoneuroscience and nanoneuropharmacology earlier, telling that the biological materials or biological facts, for example, traumatic brain injury, hypothermia, all can affect by nanoparticles. Working with different aspects of even US military and other countries, we know that external environments, for example, our soldiers are exposed to Middle East and desert. They are also breathing silica particles. And when an injury can occur on these persons, I believe situation is entirely different. This is another example. Our soldiers are living under missile explosion, so many nanoparticles in the environment. They are all affecting the biological function, and therefore they are also affecting the treatment course. This is another file picture from US military, Sandstorm. We highlighted some of the aspects of nanoparticle-induced changes in the brain, and also we need to modulate the drug treatment. This is very important. Of course, we are working with Dr. Slicker in 2004, and we have some guidance from him. So I can show you some animal experiments, how hypertension can influence the neuropathology. This is an example where the silica was exposed at 21 degrees Celsius and 33 degrees Celsius. These are hypertensive rats made in the laboratory. You can see that high environment temperature and hypertension is much more worse even when silica was introduced into the system. Another example, diabetes. You see, we measured leakage of blood-brain barrier permeability using endogenous albumin, and here you can see that diabetes only with silica intoxication, and this is diabetes only, silica only. So when the combination of nanoparticles with disease processes, we have much more extensive damage in the brain. This is a clear example that a combination of silica and diabetes has much more damage to the brain in the cerebral cortex of normal animals. At electron microscopy, we also tested the same thing. So my point is that when nanoparticles of any kind, they are introduced into the biological system, they are also affected, or their effects are altered by internal as well as external factors. This is Dr. Aaron Shikanover on ubiquitin, and some experiments we are having with him, then even the gold nanoparticles alter the ubiquitin proteasome system. I am not showing due to lack of time. So people are using nanomedicine, using different types of nanoparticles to deliver the drug. But the point is here that, of course, nano delivery of drugs can enhance the basic properties of the compound. But the point is, it may have long-lasting effect. It could be rapid penetration into the central nervous system. The drug may be less degradable. It could have wide distribution in the CNS. But what about neurotoxicity? In vivo neurotoxicity is still not very much explored. Then the question is, we have different mode of nano delivery to the drugs. The point is, if same drug is delivered using different types of nanoparticles, can we have same effect or different effects? These are the aspects we are also studying in our laboratory. Then neurotoxicity, as I told you, it depends on several factors, particularly when the nanomaterials are involved. The most important point is that health versus disease, environmental factors, genetic factors. I'm not going to show genetic factors today. Iron oxide nanoparticles, they are used nowadays with different kind of things, therapy, diagnostic, but not so much toxicity is discussed about that. Likewise, also gold neurotoxicity. And finally, I will comment something on nanodelivery of drugs. So as you can see that functionalized magnetic iron oxide nanoparticles are used in several conditions nowadays. The point is that if these particles are administered into healthy situations or in patient with cancer, can we have the same effect in both the situations? I believe no. And we tested this in animal experiments. You can see here that 38 degrees Celsius. For cancer patients, whole body hyperthermia is given, and we have mimicked in animal cases in rats. Not very similar to human cases, but quite comparable. And you can see that when they are injected in healthy animals at 4 hours, there are some changes. But 24 hours, much more dramatic changes. Then here you can see the other aspect, of course, we are looking that if we administer some kind of drugs together with these nanoparticles, can we have less changes? Because neuroprotection is one of the key ideas in our laboratory. And here we can see that there is one drug called cerebrolizin. It is not a single drug, it is a mixture of different kinds of neurotrophic factors and active peptide fragments. We are just experimenting with them. And you can see here that cerebrolizin was given 38 degrees Celsius together with these nanoparticles, 4 hours and 24 hours. There are some protection at 24 hours, not at 4 hours. Then here is the same situation. You can see that 4-hour heat stress, when they have given in situations of heat stress, the same iron oxide nanoparticles produces exacerbation of brain damage. And they were in higher doses limited but not eliminated the brain damage by the drug cerebrolizin. These are the pictures showing the same thing at electron microscopy because we believe to see the cell structures. I just show you here the cerebrolizin is a multimodal drug, and we are experimenting because whenever we have damage in the brain, no single compound or factor can be responsible. So we are using this multimodal drug to treat with them. And then we have some experiments with titanium dioxide nanowires, and this is done by Dr. Ryan Tian and Wang in the University of Arkansas because they have this US patent. So they are working with these drugs and we are using in our laboratory. So here you can see that whole body hyperthermia at 4 hours 38 degrees Celsius. Saline is like this, and when given these iron oxide nanoparticles in healthy animals, there is still damage. And then when we have given titanium dioxide level cerebrolizin, we can still protect some of the neuronal damages here. These are just showing some examples that leakage of Evans flow, iodine, brain edema, and neuronal injury were much more significantly reduced when the nanowire cerebrolizin was delivered as compared to the normal cerebrolizin. So the message is that nanowire drugs can be much more efficient than the parent compound in adverse situations. And this was one of the innovations submitted for the sleep deprivation and brain injury. And this national innovation, this US government, they have found that this technology could be one of the top 15% to my wife. So it's sitting here. So we found that probably we are going in the right direction. So then the question about gold nanoparticles, neurotoxicity. People believe that gold is completely innocuous, but this is not the case. And of course, as mentioned by my previous speaker, that size is very, very important. I'm showing you some of the results with that. This is just an example taken from the manufacturer's gold nanoparticles of different sizes. And people are using gold nanoparticles to deliver drugs. What we have done, we have used different kinds of doses that 5 nanometer size, 10 nanometer, and 40 nanometer sizes. They were given intraperitoneally, and after 24 hours, we are making the carrier. The smallest size of the gold nanoparticle produces maximum letdown of the pattern. And this pattern is quite comparable in all other doses. This is intravenous, and we have also the same. This is intracellular ventricular. The smallest gold nanoparticle size has the most damage to the brain. And also this internal carotid artery. So the point is that blood-brain barrier is much more vulnerable to the lower size of the nanoparticle, inversely proportional to the size. Then the leakage. You can see here that the leakage of endogenous albumin is quite evident in the cortical regions after different routes of the gold nanoparticles, smallest size. And this is also showing you the neuronal damages by all different kinds of routes we have used. So as mentioned by my previous speaker, routes of administration is also very, very important because that also limits the dose and size. Also, if we are getting the same results, similar results at electron microscopy, confirming our biological experiments that indeed the gold nanoparticles are damaging. So the idea is that can we have identical reduction by the same drug cerebralizing? We are working on this. I have no data at the moment to show you. But I can show you one more thing before I conclude. I told you that if we have used two different kinds of nanomaterials to level the same drug, are we going to have same results? So another 3 or 4 minutes I'm showing these data. As you know that Alzheimer's disease, the brain is completely shrunken or damaged. Nowadays, in many countries, also the United States now and China, they also label nanowire stem cells. And stem cells, when nanowire, they are much more better, effective, long-lasting, and may have better capabilities. So, well, that was also the another story when in 2013 they have given me 20% of technological. So here you can see that this is the model of Alzheimer's disease we have produced by injecting amyloid beta protein in intracerebral ventricle, and we have measured this beta protein. Sorry, and you can see here. Anyway, we have also measured tau, and you can see here that nanowire cerebralizing is most effective than the cerebralizing alone. This is one example. Then we went to the light microscopy level, and you can see that this nanowire cerebralizing induces much more better neuroprotection, leakage of albumin, astrocytic activation, and even missile neurons get better protection. Then we also went to electron microscopy, and myelin vesiculation was much more better when we have used, myelin was better protected when we have used nanowire cerebralizing. This is an example also when we combined nanowire cerebralizing and stem cells. The results with combination of stem cells and cerebralizing was much better. Then we are working with also Sir Proto. He is also a chemical Nobel Prize laureate. And then I'm showing you, we have mentioned this PLGA and also this nanowire. One of our colleagues, Dr. Giordossi, is leveling PLGA method, and we have seen that nanowire PLGA level cerebralizing is quite stable. And now here is the point. We have compared titanium nanowire cerebralizing delivery and PLGA cerebralizing delivery. What we can see in Alzheimer's disease that although they appear to be the same, but the titanium nanowire that delivers cerebralizing is much more significantly effective in same dose as compared to PLGA. We don't know how and what could be the mechanisms. To test this hypothesis again, we are working with Dr. Shelley, and he has a lot of CRF fragments, and we are leveling in both PLGA and also this nanowire to see in our Alzheimer model that our results are correct. We are going in the right direction. Also, other aspects are also included. So, I can only say that nanomedicine is the need of forward, but we must understand the neurotoxicity of nanoparticles. And there are so many factors, as mentioned by previous speakers, we must need, and particularly to regulate the external and internal factors that can contribute to nanoparticle-induced neurotoxicity. And of course, these things are in the future. Comorbidity factors must be regulated because we need to design the drugs in different ways. We are our supporters, collaboration, and friends. This is the presentation from Uppsala University, and I look forward to questions and answers. Thank you very much.
Any questions for Dr. Sharma? We have time for one.
You mentioned with the gold nanoparticles that the smaller nanoparticles cause more neurotoxicity. Is there an optimum size of neuroparticle that can penetrate the blood-brain barrier but still but have reduced neurotoxicity? And is this different for different nanoparticles like gold and FeOX?
As far as I know, the gap junction between 2 endothelial cells are 12 angstrom, and even lengthen cannot penetrate. So what could happen that these nanoparticles may stuck at the endothelial cells, may open it or damage it, and then they can go inside. But we have tested so far 5 nanometer, and we the size, 5, 20, and 50. So I can't say more.
Thank you. Thanks, Doctor. It is now time.